called the increasing decreasing test. This is how you can figure out if a function is increasing or decreasing. So I want you to think about a function. Okay? There's a function. All right. Does everyone see that from this interval a to b it's increasing? Okay. Talk to me about the derivative there. Derivative's positive. What about from b to c? What is the function doing? Function is decreasing. What about the derivative? It is negative. Okay. And then from c to d, what's the function is increasing and the derivative is positive. Okay. So this is your increasing decreasing test. So if the derivative is positive on an interval, then f is increasing. That's our first blank. So I'm writing f prime of x is greater than 0. That just means f prime is positive. If f prime is less than 0, what's another word for that? Negative. Then f is decreasing. Okay, so think about tell show. Before we start this, tell me what we have to do. Have to find the derivative, and then what are we going to figure out? Whether it's positive or negative. If you switch from positive to negative, or vice versa, negative to positive, what number do you have to pass through? Okay, so thinking about our tell show. First, you're going to find the derivative. And before you figure out where it's positive, negative, where are you going to figure out? Because you switch from positive to negative when you go through 0. So before you figure out where it's positive, negative, is you're going to figure out where is it 0. What do we call those places where the derivative is 0? Critical point. Okay, so then you're going to set up, this is new, you're going to set up what's called a sign chart. And the sign chart is going to determine when your derivative is positive or negative. All right, so our first step is to find the derivative. It's an easy one. What's the derivative here? Okay, so we want to know where is this positive or negative. It's helpful first to figure out where it's 0. Is everyone clear why we're going to do 0 first? Okay. Oh, you said it equal to 0. Yep, we're finding when the derivative equals 0. Okay, I see some GCFs. 12 and an x, right? So that gives me x squared minus x minus 2. What I didn't write up here was equal 0. Okay, how am I going to solve? Yeah, I'm factoring. Two numbers that multiply to -2 and add to -1. They multiply to -2, add to -1. Yep, -2 and +1. Okay. Yep, so there's 3 solutions. Oh, yep, thank you. +1. Thank you. Okay, there are 3 solutions. What are the 3 solutions? And 0. Do you guys see that one's 0 right there? Okay. So those are the 3 solutions. Okay, so now we're going to make our sign chart. Here's what you want to do for your sign chart. You're just going to make a number line. And you need to put the 3 numbers where the derivative hits 0 on the number line. So -1 is the one on the left, and then 0, and then 2. Don't worry about the spacing. They just need to be in order. And now what you're going to do is you're going to figure out what is the derivative doing in each of these intervals. How many intervals are there here? There's not 3. Intervals are spaces. How many spaces are on this number line? There's 4. You have a space less than -1. Okay, you have a space between -1 and 0, a space between 0 and 2, and a space above 2. You want to know what the sign of the derivative is. So you're going to take a number in this interval, and you're going to substitute it into the derivative function. Okay? Yep. You want to try to pick some convenient numbers. Okay? Let's start here. This is the easy one, between 0 and 2. What's the convenient number between 0 and 2? Okay, so plug 1 back into your derivative. All we care about is positive or negative. Okay? So 1 cubed times 12. I'm doing this interval first. We're doing positive 1. So 1 cubed times 12 is 12. 1 squared times 12 is 12. So 12 minus 12 is 0. Minus 24 is -12, right? So I'm just going to put a negative sign in that space there. All I know is that the derivative between 0 and 2 is negative. So just picking one interval. So I'm going to pause this here. And what I want you to do is I want you to pick a number in the other intervals. Again, plug in the derivative, see what you can come up with. Yes. Okay, so now we just have to, so we have our sign chart. Now we're ready to answer the question. This means this first interval, from -infinity to -1, the derivative is always negative. So what can you say about the function? What is the function doing there? The derivative is, it's decreasing. Where else is it decreasing? Yeah, so it's decreasing from -infinity to -1. Not at -1, because at -1, what is the derivative? Do you remember? Yeah, the derivative is 0. That's why we're not including -1 in the answer. Where else is it decreasing? On the interval from 0 to 2, the open interval. That's that union symbol, meaning and. Yep. And where does the function increase? -1 to 0 and 2 to infinity. Okay, so the first derivative test is one of a couple. There's a couple different tests that you can use to find local max or min. So we're going to add that. That's a slash there. The first derivative test is what you use to find your local max and min. All right, so it says suppose that C is a blank number of a blank function f. So C is going to be a critical number. So what's happening at C? The derivative is 0 or does not exist. Good. So C is one of our critical numbers. And what type of functions are we dealing with? Only continuous, right? We're only talking about continuous functions. Right. All right, so part A, if f prime changes from positive to negative, if f prime changes from positive to negative at C, then f has a local what? Then f has a local maximum. Right, it's not the absolute maximum, but it's in that nearby area, it's the maximum. Yep. So part B is going to be the vice versa. If f changes from, what do you think? Good. From negative to positive, what do you think? Local min. Good. So here we're just going to quickly sketch. Yep. We're just going to quickly sketch. There's an example of a local max. Right? And you can see the derivative changing. If I'm doing my pencil test, the derivative changes from positive to negative. Over here. And I'm doing something crazy so you can see the locals, right? Right here, the derivative changes from negative to positive local min. Right here, derivative changes from negative to positive, another local min. So part C says, what happens if f prime does not change sign? So it's positive on both sides or negative on both sides. Then it's neither. It's not a local max or a local min. So a quick picture of what that might look like. You could have a positive derivative. You could hit 0, and then you could still have a positive derivative. Does everyone see that? Right here, the derivative is 0, but it's positive there and positive there. So that's an example. It's not a max or a min. It's a critical point, but it's not a max or a min. Likewise, you could have negative and negative. Right here, the derivative is hitting 0. Over here, the derivative is negative. Over there, the derivative is negative. Even though that's a critical point, it is neither local max or min. Yep, so we're going to skip over D&E right now, and we're just going to go straight to example 2. All right, so the text says, use calculus to find the local max and min values of the function. Okay, so tell me what we're going to do first. Yeah, we're going to find the derivative. Okay, so once we find the derivative, yeah. If we're talking about local max, almost. Find when what equals 0. Good. What's that called when the derivative equals 0? Okay, so where else should we look? Besides the derivative, where the derivative does not exist. These are critical points. We're finding all of our critical points. But we still want to do that, right? Okay, then we're going to make our sign chart just like we did before. So remember, only the critical numbers go on your sign chart. And then how do you, okay, so when you make your sign chart, all of your critical points are going on your sign chart and your endpoints, because they could also be max or min, thinking back to absolute values. So once you put your critical points and your endpoints on your sign chart, you are going to pick a number in each interval to analyze. You're analyzing the sign, that's why it's called a sign chart, of what? The sign of the derivative. We want to know if the derivative is positive or negative. So that's how you make a sign chart. You're putting your critical points and endpoints, if there are some, on a number line, and then you're analyzing the derivative in each space. Is it positive or negative? So our last step in our tell show, after you've made your sign chart, then you need to analyze your sign chart. Right. So you're analyzing your sign chart to answer the question. And the question here is, what are the local max and min? And remember, local max and min happen when the derivative does what? When the derivative changes sign. So we're looking for where does the derivative change sign? I'm going to use delta, changes sign. F of x, f prime of x, excuse me, changes sign. All right, so let's go through. First step, find f prime of x. Okay? So we're doing show. F prime of x is you got it, 1 plus 2 cosine x. Okay. Yep, we're setting that equal to 0. Will that ever not exist? No, cosine is continuous. So we're not worried about D&E at all, but we are going to figure out what equals 0. So I'm going to subtract 1 from both sides and divide by 2. And I'm looking for all the places on my unit circle where cosine x equals negative 1/2. All right, so these two values are 2 pi over 3 and 4 pi over 3. So that was part 2 of our tell-show step. So next part, we are making a sign chart. We need the critical points and the endpoints. So remember, a sign chart looks like a number line. Yep, so we're starting at 0. And then next we have 2 pi over 3. And then 4 pi over 3. And then 2 pi. So this time there's only 3 intervals. Remember, there's nothing to the left of 0 or 2 pi because those are endpoints. We're not going out to infinity. Sorry about what I'm saying. So right now you're going to pick a convenient number in each of the 3 intervals, plug it into f prime to figure out the signs. Okay, so we have our sign chart. We see the intervals. So now we're going to analyze our sign chart to find our local max and min. Okay, so we're analyzing, we're looking for the changes. So I see that at 2 pi over 3, my derivative is switching from positive to negative. So what conclusion can I make? What's happening there? Well, it's positive and then it switches to negative. It's a, what kind of minimum? It's a local min, right? So 2 pi, sorry, it's a maximum. Did we say minimum? Yep, I'm sorry. You're right, maximum. Yep, 2 pi over 3 is a local maximum. If you want full credit for this question on FRQ, you have to say why. How do we know it's a local maximum? What is positive? Good, because, okay, and you can write math, you don't have to write the word derivative, because f prime changes, sure, from positive to negative. And you can abbreviate, they read those abbreviations. Yes, yep, that's fine. Sorry. Yeah, so now 4 pi over 3 is a local min, and you have to state how you know that. You have to cite your evidence from the text. Good, because f prime changes from negative to positive. That is an acceptable answer on the AP exam. Yeah, so 0 and 2 pi, right, what are you doing there? So let's talk about those. This is what we skipped in part D and E, but we can analyze this, okay? So let's look at our sign chart. We don't know what the output is at 0, and let's not bother calculating it, but between 0 and 2 pi, you're always increasing. So imagine this, if I were to graph this. If I start at 0, I don't know where I'm starting. I don't know how high or low, but I do know that I'm increasing. And then at 2 pi over 3, I start decreasing. And then at 4 pi over 3, I start increasing again. Okay? I don't know if that's what the graph looks like, but I'm just sort of sketching an idea of what's happening here. So what do you think is at 0, a local max or min? A local min, right? So you can also analyze endpoints. Now, one of these is the absolute value. I mean, not the absolute max or min, but that's not the question. So we're not going to analyze that, okay? So you're right, we're not done. 0 is a local min, right? And 2 pi, you increase to get to 2 pi, so it's a local max. Good, so we also need to add that. So for the endpoints, this is what we skipped in part D and E. The endpoints, you can't analyze the change, but you're just analyzing what's happening near them. So 0 is a local min because the derivative is positive to the right of 0. We can't talk about the change because we don't know what's happening to the left of 0. And then you guys also told me 2 pi is a local max because the derivative is positive to the left of 2 pi. Okay, so right here we've got a very technical definition of concavity. You guys familiar with concave up, concave down? Okay. If the graph of f lies blank, all of its tangent on an interval, then it's called concave up. Okay? So we're going to sketch a concave up. All right, is the graph above or below all of the tangent lines? If I were to sketch a tangent line, the graphs of, do you guys see that? Any tangent line, I can do one on the other side. Here's the horizontal tangent line. Do you see how that graph in blue is always above the tangent lines? Okay, that's the technical definition of concave up. Good. So below would be concave down, yep. And we can sketch a quick example. There's an example of concave down, and I can convince you by drawing a couple different tangent lines that function is always below those blue tangent lines. All right, so the concavity test says if what is above 0? What is that? The second derivative, okay? The concavity test uses the second derivative. If f double prime is positive, then the graph is concave up. Positive is concave up. And if f double prime is negative, then the graph is concave down. Okay, so a point P is called an inflection point. If, this should say f prime, the derivative has to be 0, and the curve has to change from concave up to concave down, or vice versa, from concave down to concave up. I'm going to sketch just a quick example. It's like the one we saw previously. This is an example of an inflection point. So right here, the derivative is 0 because the tangent line is horizontal. Do you see that to the left it's concave down, but to the right it's concave up? But this is an example where the first derivative, it's always increasing. So the first derivative doesn't change sign, positive to positive. It is neither a local max or min. But it is a point of inflection. The concavity is changing from concave down to concave up. Okay, so we're going to do example 3 together. So we have this function, f of x equals x to the 4th minus 4x cubed. Notice how there's no endpoints. So we are looking on the domain all real numbers. So ABC, we're going to put everything together. We're going to find the intervals on which f is increasing or decreasing. We're going to find the local max and min. And we're going to find the concavity and inflection points. Okay? So let's just look at part A, and let's do a tell show. All right, so let's start with the tell side. Find intervals on which f is increasing or decreasing. So if you're thinking about increasing, decreasing, what do you want to analyze? Okay, so if we want to find intervals on which f is increasing or decreasing, we want to analyze the first derivative. So what are we going to do? Yeah, we're going to start by finding the first derivative. And if we're talking about increasing or decreasing, we want to know where the first derivative is positive or negative. But it'd be a lot easier to find where it equals 0. Or does not exist, right? Because a corner is also an example of increasing and decreasing, does not exist. So we're going to find, what are those called? Good, we're finding critical points. We're going to find all of our critical points. And then we're going to take our critical points and put them where? on a sign chart, right? So we're going to put our critical points on a sign chart. And after we have those numbers on a sign chart, what else are we going to put on the sign chart? Analyzing which derivative? Which derivative? Yep. So you're going to pick values in each interval, and you're going to evaluate the first derivative, and all we're going to be concerned about is whether it's positive or negative. So you're going to note positive or negative on your sign chart. Okay, but when you do a sign chart, you're not done. What do you have to do after you make your sign chart? You have to analyze it. So that's your last part. So we're going to analyze our sign chart. The question was, where is the function increasing or decreasing? So what are we looking for? Yeah, we're looking for intervals. In this question, we're looking for intervals where f prime is positive or negative. That'll tell us if the function is increasing or decreasing. Okay, so now we're finally ready to do our show. So first we're going to find the derivative. It's not too bad. What's the derivative here? Good. Would this ever not exist? Yeah, it's a polynomial function. So we're just going to set it equal to 0. Okay, I see GCF. Good. 4x squared, leaving behind x minus 3. And I see 2 solutions for x. Good. 0 and positive 3 are the only critical points. Okay, so now we have our critical points. We're going to make a sign chart, and we're putting our critical points. There's no end points, so we're putting 0 and 3. So there's how many intervals? 3, right? There's the one between 0 and 3, but there's also one to the left of 0 and one to the right of 3. So now we're going to pick convenient numbers in each interval. We're going to substitute them in, and we're just going to note on our sign chart, is the derivative positive or negative? And I always like to write down what I'm doing. I'm doing the first derivative, and in each spot I'm going to write positive or negative. All right, so now we have our values on our sign chart, so the intervals go negative, negative, positive. So now we're going to analyze the sign chart. Make sure you're answering the question. So the question here was, find the intervals on which f is increasing or decreasing. Okay, so analyzing your sign chart, where is the function increasing? Good. The function is increasing. So you can abbreviate INCR. The function is increasing on the interval 3 to infinity. Okay, I need some evidence from the text. That is your claim. What is your evidence? The slope is positive. What's another word for slope in calculus? Yeah. Yeah, if the derivative is positive on that interval, so it's increasing on that interval. Where is the function decreasing? Negative infinity to, not just negative infinity to 0, to 3, okay? Is it decreasing at 0? Okay, so we are decreasing on 2 intervals, negative infinity to 0 and 0 to 3. That's our claim. And our evidence is that on those intervals, the derivative is negative. So at 0, for a moment, at 0, you're momentarily not decreasing. So we're going to leave 0 out of it. Okay, so part B says find the local max and min values of f. So we're just going to talk through this because it repeats a lot. So if we are finding local max and min, what would we do first? If we're finding local max and min, which happen when the derivative does what? The first derivative changes sign. So we would need to find the first derivative. We would then need to find the critical points. We would then need to make a sign chart. See, we've already done all this. We would then need to put our values in to complete our sign chart. So steps 1, 2, 3, and 4, the only part that's going to change is the analysis. We're analyzing something different. So we've actually already done all the work for part B. Okay? So at 0, does the sign of the first derivative change? It's neither local max nor min. What about at 3? Yep. Your derivative, draw it out. Your derivative changes from negative to positive, so it is a local min. Okay? So this is part B. So we actually didn't have to do any work. Part B. So x equals 3 is a local min because, what's our evidence? Yeah, and you have to be specific. It changes from negative to positive. You can't just say it changes sign, because that would just tell me it was a local max or min. Yep, okay, so now in part C, we're asked to find the intervals of concavity. If we're looking at intervals of concavity, what are we analyzing? We're analyzing the second derivative, okay? So our telshow is going to change here. What would we need to find? We have to find the second derivative, right? So this is part C. We do have to do a fresh telshow here. Okay, so we do need to find the second derivative. I'm just writing f double prime. We're finding the second derivative. Well, will that tell you the concavity? What do you have to do? We want to analyze the signs, right? The signs change when you go through what number? Yep. So part 2, yep, is you're going to set the second derivative equal to 0. And then you're going to make a sign chart. And just like we did above, we're going to analyze. That's a z. Okay, so to find the second derivative, we start with the first derivative. What was the first derivative? Okay, so then the second derivative is the derivative of that, 12x squared minus 24x, right? So we're going to set that equal to 0. And there's a GCF. Yep. And where does x equal 0? Or where does the function equal 0? 0 and positive 2. Zero and positive 2. So we're making a new sign chart. These are the only two numbers on it. That's where our second derivative is 0. And if we want to find the concavity, what are we going to analyze? Which derivative? Second derivative. We're going to analyze the second derivative. So we're going to pick a convenient value, and we're just going to determine if the sign is positive or negative. Okay, so there's our sign chart. So our last step is to analyze it. Remember, the question is find the intervals of concavity and the inflection points. Okay, so where is the function concave up? Good. So the function is concave up on two intervals, from negative infinity to 0 and 2 to infinity. That's our claim. What's our evidence? Good, because that's where the second derivative is positive. So now we're going to answer, where is the function concave down? Good. It's concave down on 0 to 2. That's your claim. What's your evidence? The sign of what? Not the derivative. The derivative of the derivative. What would be a better way to say that? Second derivative. The second derivative is what? Negative on that interval. Okay, you have to be specific if you're going to get points on your FRQ. All right, so part C, yeah, we already did all the work. We have the intervals of concavity. We need the inflection points. Inflection points happen when what? Not the derivative. When the second derivative point of inflection okay, no. So the last question is point of inflection. There's two criteria for a point of inflection. First criteria is that your first derivative is 0. The second criteria is that your second derivative changes sign. Okay? So our first derivative is 0 at 0 and 3. The second derivative changes at 0 and 2. But only one of those points meets both criteria, and that's 0. So x equals 0 is an inflection point because there's two criteria. Criteria 1, f prime of 0 equals 0. It was one of her critical points. And then our second criteria is that f double prime changes sign at 0. Both criteria have to be met to be an inflection point. So 0 is the only point of inflection. All right, so last thing you need to do, this is homework, is you're going to do example 4. All right, we'll talk about it when we come into class on Tuesday. We'll check it together. And then there's one AP multiple choice question below number 4 that I also want you to attempt, and we'll talk about these when we return.